Hello students, now let us start with the second part of this particular concept called as self-induction, right? Now students, in the previous module, we have already covered what is self-induction and we have also defined self-induction. Now let us revise. Now what is self-induction? It is nothing but the phenomena of production of induced EMF in a coil due to the change in current in the same coil is called as self-induction. So what is the definition? The phenomena of production of an induced EMF in a coil due to the change in current in the same coil is called as self-induction, right? Now students, we know that once current was changing, so flux was changing, right? And because of the change in flux, EMF was getting induced in it, right? So in this case, I can say there is a definite relation between the flux which is produced and the current that was passing through the coil, or I can say the magnetic flux phi which is linked with the coil, it is directly proportional to the value of current I which is passing through that particular coil, and therefore I can say phi is directly proportional to I. Right? Now here there is a proportionality sign, so I can introduce a constant. So what will I get? I'll get phi, it is equal to capital L into I. Now what is capital L? This capital L is constant of proportionality and it is also referred as coefficient of self-induction or self-inductance. Right? Now let us take this last equation in. Now over here I can say there is a relation between phi and I. Now if I, that is current, is changing with respect to time, now because of this change in current, the value of flux will also change, right? Now again, as flux is changing with respect to time, an EMF will get induced in the coil, and we know the relation for EMF induced and the rate of change of flux. What is the relation? We know that E, it is equal to minus of d phi by dt, right? What is phi? Phi is flux and it is changing with respect to time. Now students, we know value of phi. What is value of phi? Phi is nothing but equal to Li in this situation. So I'll be substituting this value over here. So what will I get? I'll get E, it is equal to minus of d dt of Li. Right? Now let us take this last equation ahead. Now students, over here, what is L? L is constant of proportionality and it is referred as coefficient of self-induction, or it is also referred as self-inductance. And since it is constant, it will come out of the differentiation sign. So what will I get? I'll get E, it is equal to minus of L into di by dt. Right? Now students, see this equation carefully. Now what is E? E is induced EMF. What is L? L is nothing but coefficient of self-induction. And what is di by dt? Di by dt is nothing but change in current with respect to time, right? And you can see there is a negative sign over there. And what does this negative sign indicates? This negative sign indicates that this induced EMF is opposing the change of current in the same coil, right? And why it is opposing the change of current in the same coil? Because this rate of change of current in the coil is the reason behind induced EMF. Right? And according to Lenz's law, induced EMF will always oppose the cause producing. That's why we are having negative sign over here. Right? Now let us move further. Let us start with the next part of this particular module, that is coefficient of self-induction or self-inductance, that is capital L. Now students, we know the relation. What is the relation? E, it is equal to minus of L into di by dt. Right? Now if I take the magnitude, so what will I get? I'll get mod of E, it is equal to L into di by dt. Now I'll transfer this di by dt on that side. So what will I get? I'll get capital L, it is equal to E upon di by dt, or rather L, it is equal to mod of E upon di by dt. Now from this particular formula, we can define coefficient of self-induction or self-inductance. Now see the formula carefully. So I can say coefficient of self-inductance, that is capital L, of a coil, it is equal to EMF induced, or rather magnitude of EMF induced in the coil due to unit rate of change of current in the same coil. Right? So what is the definition? It is equal to the magnitude of EMF induced in the coil due to the unit rate of change of current in the same coil. And this is nothing but the definition of coefficient of self-induction or self-inductance, which is given by symbol capital L. Right? Now let us move further. This value of L increases significantly when we are using materials like iron, nickel or cobalt as a core. And this self-inductance also depends upon the shape and the size of the coil also. Right? Now these points are very important, kindly note it down. Now let us move further and let us write down the unit. Now we know the basic relation. What is the basic relation? L, it is equal to mod of E upon di by dt. Right? What is E? E is induced EMF. So what is the unit for it? Unit for it is volts, right? And what is unit of di by dt? Unit of di by dt will be ampere per second, right? Now this second will go upstairs. So what will I get? I'll get volt second upon ampere, right? And this volt second upon ampere is basically referred as Henry, which is represented by symbol capital H. Now see these two terms carefully, volt upon ampere. Now students, volt upon ampere according to Ohm's law, it should be equal to ohm. So it is also having a unit called as ohm into second, right? So what are the units? Units are Henry, and it is also ohm second, right? Now let us move further. Let us write down the dimensions, and the dimensions of capital L are m raised to 1, L raised to 2, T raised to power minus 2, and I raised to power minus 2. Now let us move further and let us define 1 Henry in this particular situation. Right? Now students, we know the basic relation L, it is equal to mod of E upon di by dt. Now if I place value of E as 1 volt and di by dt as 1 ampere per second. Now if I substitute these two values over here, what will I get? I'll get capital L, it is equal to 1 Henry. Right? So let me define this particular term. So the coefficient of self-inductance or coefficient of self-induction, it is said to be 1 Henry when EMF induced is equal to 1 volt and the current in the coil is changing at the rate of 1 ampere per second, right? So let us write it technically. Self-inductance of a coil is 1 Henry when EMF of 1 volt is induced in the coil when the current in the same coil is changing at the rate of 1 ampere per second. Right? So students, in this particular module, we have discussed about the mathematical part which is related to self-induction. So that's it for this particular module. I'll see you in the next module. Till then, keep learning.